Hello guys, welcome back to your favorite and India's most affordable learning platform, Physics Wallah. So in the last session we completed the circular motion. So the motion in a vertical circular motion, right? So today we are going to start the new chapter, that is the work, energy and power. So this chapter is going to be very important for your competitive examinations. So compulsory, one or two questions will come from this chapter. And whatever the concepts that you are going to learn in this chapter, so will be useful in other chapters as well, especially applying the conservation of mechanical energy or finding the work done. So whatever the work done that we are discussing here, so again in electrostatics of class 12th, we'll come across what is the work done by this charge and what is the work done by moving this charge from this point to the another point. So like that, so all the topics will be interlinked with the work, energy, power. Other topics will be interlinked with this chapter. So that's why you should learn the work, energy, power compulsory as a prerequisite for other chapters as well. Okay, chalo. So today it's going to be just the basics, the first class of the work, energy, power. So mostly I am going to take some 5 to 6 lectures for the work, energy, power. Okay, so we'll discuss all the concepts in detail and we'll solve n number of numericals. So, okay, clear? So first let's see what are our targets today. So only 2 targets for today's class: work done by the constant force and work done by the variable force. Clear? So I just need your attention guys for the next 1 hour. Just be with me, avoid all the disturbances around you. Okay, chal. So let's begin the today's session with very high positive energy. So first, what is work done? You already learned the work chapter in grade 9th, right? So basics of work done, what is power and what is work energy theorem. So you have already having basic idea. You have the basic idea, right? So now, so just let's go through the basics first, then we'll go for the advanced concepts again. So what is work done? It's a scalar product of the force and displacement, right? So the work done will be equals to force into the displacement. Let the displacement is denoted with S or X, okay, or D, your wish. So this is a force into force dot displacement. This is the dot product of force into displacement. Scalar product means it's a dot product, right? So it's a dot product of force and displacement, right? So and dot product of 2 vector quantities results in a scalar quantity. So the work done is a scalar quantity. The work done is a scalar quantity. And then, so the work done will be equals to Fs cos theta. The work done will be equals to, so just F dot S means Fs cos theta. So if the force is applied on the body like this and the body has displaced from here to here, so what is the angle between force and displacement? Theta. So where theta is a angle between force and displacement. So theta is the angle between force and displacement. So clear this part? Understood a basic thing. So the same thing I wrote here. So work done is equals to F dot S, which is Fs cos theta. So F means magnitude of F. So and S means magnitude of S, we mean, right? And then, so here you can write this formula in 2 different ways. See here. So let me add the another slide. See here. So let me take this one. So consider this is a surface, and then there is an object is placed. So this is the object of mass m on which the force is applied. Consider this is a force is applied at an angle theta, right? So and the body has displaced from here to some point here. So let it be here. So the displacement is this side. So now we can write force work done will be equals to, the basic formula is Fs cos theta, Fs cos theta, right, or F dot S. So shall I write it as, what is the force component along the displacement? The force component along the displacement is, this F will have two components. One component this side, one, see, F will have two components. One is F sin theta this side, and theta is there this side. So therefore F cos theta this side. So the force component along the displacement is F cos theta. So I can write this as, so the force F cos theta into the displacement, which is nothing but the component of force in the direction of displacement. It's the component of force in the direction of displacement, into displacement. Shall we write the component of force in the direction of displacement, F cos theta, into the displacement, which is nothing but S. Shall we write like this? That means F cos theta into S. What is F cos theta? It is the component of force along the displacement. So this is one way. And the other way, so that is, let's take, so here is a surface, and then the object is of mass m is placed, and then it is displaced from here to here. So this is of mass m, and then some force F is applied on it, so at an angle with the horizontal theta. So or else let's take this force to this side. So this angle is going to be theta. So now see here, shall I write it like, so here this is the force component and this is the displacement. So if it is a displacement, this displacement is making some angle theta with this. So if I consider this is a frame of reference, the displacement will have two components. Shall I say, so the displacement component along the force is S cos theta, yes or no? So this side theta is there, so that's why this side cos theta, S cos theta will come, and this side S sin theta will come. Just I am changing the frame of reference. If I consider this as my x-axis and this as my y-axis, and S is between the x-axis and y-axis, right? So that's why S will have two components. Wherever the theta is there, that side will get the S cos theta, and theta is not there, this side S sin theta will get. So now see here, so shall I write the work done is equals to, so here force into S cos theta. So what is this? Force into, so shall I write this S cos theta as, this is the displacement in the direction of force. S cos theta is the displacement in the direction of force. S cos theta is nothing but the displacement. S cos theta is nothing but displacement in the direction of force. So that means the work done, you can write it as force in the direction of displacement into displacement, or force into displacement in the direction of force. Force into the displacement in the direction of force. So both are same. The work done is equals to Fs cos theta. You can write it as F cos theta into S, or F into S cos theta. Clear? Understood the concept, guys? So this is a basic formula. And what are the units? So let's discuss about the units. So the SI unit of the work is, so Newton meter. So the work done is equals to force in dot displacement, right? So force units are joules, sorry, Newton, and displacement is meter. So Newton meter, or which is also called joule. So this is the SI unit, and the CGS unit is dyne centimeter. So Newton CGS is dyne, and meter it is centimeter for CGS, or which is also called erg. So where 1 joule is equals to 10 to the power 7 erg. 1 joule is equals to 10 to the power 7 erg. Clear? Understood this part, guys? Everyone? No doubts here? So basic things. So just we have to remember the formula and its units. Okay? Chalo. So what are the special cases now? So work done is equals to Fs cos theta. So if the angle between the force and displacement is 0, so then the work done will be equals to Fs cos 0. So the cos 0 value is 1, so that it's going to be the work done is equals to Fs. So we can say that the maximum work is done in this case, right? So which is Fs. So this is a force into displacement directly, we can write. And then, so theta is equals to 180. So the work done is equals to Fs cos 180, right? So which is equals to, so what is cos 180 value is -1. So which is work done is equals to minus 180. So minus Fs, sorry. So this is the minimum work done, right? And then, so theta is equals to 90. So work done will be equals to cos 90 is 0. So the work done will be equals to 0. So if the theta is equals to 90, that means the angle between force and displacement is 90 degrees. So then the work done will be equals to 0. So what is theta here? The theta is a angle between force and displacement. Theta is the angle between force and displacement. Clear, guys? Understood this part? Chalo. So the first case, so you can have the example also. Let's suppose, so here is the object of mass m and you applied the force on it, so that the object has moved from here to here. So this is a mass m. So see here, the force and displacement are in the same direction here. Force and displacement are in the same direction. Now, so in the second case, let's say this is the inclined plane. Consider this is the inclined plane. So now, so this side, here is the mass m and you are applying the force F, but the object is sliding down. The object is sliding down, let's suppose, because of the more inclined. So it is sliding down, but you are applying the force upside. So the force and displacement are in opposite directions here. Theta 180 degrees. And then if the object is placed here, and then so object is moving right side, but you are applying the force upside. So force and displacement are perpendicular to each other in this case, right? Clear? These are the three special cases of work done. Understood, guys? Chalo. So let's move further. So let's take the questions, the simple questions. Let's solve one by one. So we'll understand the concepts through questions. We'll solve at least some 13-14 questions in this session. Okay. So a body of mass 5 kg is placed at the origin and can move only on the x-axis. So it can only move on the x-axis. So this is a mass of body 5 kg. It can only move along the x-axis. A force of 10 newtons is acting. So a force of 10 newtons is acting on it in a direction making angle 60 degrees with the x-axis. So see here. So the force acting on it is 10 newtons. So making an angle 60 degrees with the x-axis. Okay. So then, and displaces it along the x-axis by 4 meters. So it displaced it from here to here by 4 meters. So this is a 5 kg block and this distance displacement is 4 meters. What is the work done? So the work done is equals to F dot S, right? Which we can write Fs cos theta. So Fs cos theta, right? So what is the force here? 10 newtons force. And displacement, how much it is displaced? 4 meters in the x direction. And cos theta, the angle between force and displacement is 60. So therefore cos 60 degrees. So therefore the work done is equals to 10 into 4, 40 into, so this is 1 by 2. So which is work done is equals to 20 joules. The work done is equals to 20 joules. Option 4 is the correct one. Clear? Simple question. Chalo, let's move further. Let's go for the next question. Read the question, guys. A body moves a distance of 10 meters along a straight line under the action of force of 5 newtons. If the work done is 25 joules, so the angle between the force and the direction of the motion of the body is, see here. So let's draw the diagram. So consider, so this is a object which is of mass not given, let it be m. So it moved along the straight line, that means from here to here. So this object has moved 10 meters. Fine. So then upon the action of force 5 newtons. So the force acting on it is 5 newtons. right? So if the work done is, the work done formula is what? F dot S, yes or no? So here the work done is equals to, we can write Fs cos theta. So in the given question, the work done is given. So how much? 25 joules, which is equals to, what is the force? 5. What is the displacement of the body? 10 meters into cos theta, right? So from here, so I can write 25 or else 5 ones are 5 5s are. So cos theta is equals to 5 by 10, right? 5 by 10. So theta is equals to, or cos theta is equals to 1 by 2. So theta must be equals to 60 degrees, right? Cos 60 is 1 by 2. So therefore the theta theta must be equals to 60 degrees. Clear? Understood, guys? Sorry. Chalo. Next, the question number 3. A body is being raised to a height h from the surface of the earth. What is the sign of the work done by the applied force and the gravitational force respectively? See here. So first, this is a earth surface and here is a body of mass m. So now a body is being raised to a height h. So from here, so this body is being raised to some height h. This is a mass m. It is being raised to some height h from the surface of the earth. So if it is being raised to some height means, let's suppose this is a horizontal surface. You are raising this object means you are applying the force upward. The applied force is upward. So which means the force is upward and the displacement h is also upward, right? So in this case, the work done by the applied force will be equals to force into displacement into cos theta. So what is the force we are applying? F. So what is the displacement? Height h. And then force and displacement both are in same direction. So therefore cos 0 is the angle between them. So which is nothing but F into h. So they are asking whether it is positive or negative. The work done by applied force is positive because force and displacement both are in the same direction. Now consider the second scenario. Consider the second scenario. See here, this is the surface and here is the mass m is placed. So now, so if you are applying the applied force is upside, body is being raised to this point m, so of height h. So now the gravitational force, so to which side the gravitational force will act? Mg downside. The gravitational force is mg, its weight. And so see, if you observe, the body displacement is upward and then so body's the gravitational force is downward. So these two are opposite to each other. So here the work done is equals to F dot S and then which is Fs cos theta. So here the force is gravitational force mg and then h is h, s is h, and then the theta is 180 degrees I can say, because the force is downward, displacement is upward. Which force? The gravitational force is downward. So that's why it's going to be simply minus mgh. So that means the work done will be negative in this case. So the work done in the applied force case, it is positive. So the work done by the applied force is positive and work done by the gravitational force is negative. So positive positive, no. Positive negative, yes. Negative positive, no. So negative negative, no. So first one is positive, second one negative. Clear? Chal. So let's go for the next question. A box of mass 1 kg is pulled on a horizontal surface, horizontal plane of length 1 meter by a force of 8 newtons. So then it is raised vertically to a height of 2 meters at constant speed. So the net work done is, see here. So this is the horizontal plane. Okay. So there is a mass of 1 kg body, right? So it is pulled. So this side it is pulled by applying a force of 8 newtons, so that it displaced by 1 meter. So from here to here, let's suppose it displaced by 1 meter. So from here to here, it displaced by 1 meter, let's suppose. So then it is being raised vertically. So from here it is raised vertically. So that means it is raised till some height, 2 meters height. Okay, so that means you have to apply the force in this direction. So what is the total work done that they are asking? So first one, the work done in the horizontal case, let's find it. Let's find. So what is the work done in the horizontal case? So the work done in so let it be case 1, let it be case 2. So write it like this. So in the first case, the work done is equals to Fs cos theta. The force applied is 8 newtons into the displacement is 1 meter, and force and displacement both are in the same direction. So therefore cos 0. So therefore this is 8 joules. So the work done in the first case is 8 joule. So now once the body is reached here, so now it is being raised to 2 meters, right? So what is the work done in the second case now? So it is raised at constant speed. At constant speed means we know that downward 1g is the gravitational force x. So to move it constantly upward, so with the constant speed, so the force, the applied force must be which is equals to the gravitational force. What is applied force? If you apply 1g, so then only it move upward. So therefore the work done in the second case, it's going to be, so the Fs cos theta. So what is the applied force? The applied force is equals to the gravitational force. That's why 1g into, so how much displacement it is moved? 2 into the cos 0. The applied force, see, gravitational force is downward. They are not asking what is the work done by the gravitational force in this case. It's not being raised upwards due to the gravitational force. It's being raised upward due to the applied force which is equals to gravitational force. So that means the applied force is upwards. So and displacement is also upward. Don't take 180 degrees here. So this is 1 into 10 into 2. So which is nothing but 20 joules. So therefore, so the total net work done, the net work done is equals to the work done in the first case plus the work done in the second case. So which is 8 joule plus 20 joule. So which is nothing but the 28 joule is the net work done. So option A is the correct answer, guys. Clear? Understood, everyone? Chalo. So let's move further. So let's take the next question, question number 5. Simple questions, so let's move faster. Okay. So a horizontal force of 5 newtons is required to maintain a velocity 2 meters per second for a block of 10 kg mass sliding over a rough surface. So here, consider here is a rough surface. So and then there is a mass of block 10 kg, right? And then what they said, a horizontal force 5 newtons is required. This is a rough surface to maintain a velocity 2 meters per second, constant velocity 2 meters per second. So over a rough surface. So the work done by this force in 1 minute is, so they are asking what is the work done by this force in 1 minute. So see here, the first thing is the work done is equals to force into displacement into cos theta, right? So we know the force, we don't know the displacement. So how do you find? See, so it is sliding over the rough surface. So the force we have to find in 1 minute, right? So we know that the velocity is equals to displacement by time. Displacement by time. We know the velocity and time here. So let's find the displacement. So the displacement is equals to velocity into the time taken. What is the velocity here? So the velocity is 2 meters per second and the time is, so 1 minute they said I am taking 60 seconds. So which is nothing but 120 meters is a displacement. So therefore the force is 5 newtons, the displacement is 120 and they both are in the same direction, which is cos 0. So that's why this is going to be 600 joules. So option A is the correct one, 600 joules. Clear, guys? Chalo. So next question. Let's see the next question. What's the question says? Find the work done by the external force of 50 newtons and frictional force when 10 kg block displaced by 5 meters. See here. So two cases. First let's find the work done by the applied force. Simple thing. So this is a 10 kg block and 50 newtons force is applied this side, so that the body displaces by 5 meters. So this is a 10 kg body, so which displaces by 5 meters. So obviously the work done will be equals to Fs cos theta. The force, what is the applied force? 50 newtons, and the body will displace in the direction of the force applied. So that's why the displacement is 5. So the cos 0 degrees, right? So this is going to be 250 joules. So the work done by applied force, the first one they asked, the work done by the applied force is external force is 250 joules. So in everywhere 250, 250, 250. So you can't decide the options. Now, so as it is a rough surface, so the friction is acting this side. So the friction is acting on it this side. So let this friction be the limiting friction. We don't know what kind of friction it is. So let's say, so the limiting friction. So what is the limiting friction? Let's find it. What is that? So mu into n. So mu into here normal is equals to 10g, its weight, right? So mu into, so mg, let's write. So mu is 0.1, mass is 10, g is 10. So this is going to be 10 Newton. So that means the F limiting is acting this side. So how much? The 10 Newtons. Now, so we need the work done by the friction. So the work done by the friction. So simply write this way. So the frictional force, so the Fs cos theta. Fs cos theta. Always follow this formula. So here the work done by which friction we are, the work done by which force we are finding? Due to the friction, right? So what is the frictional force? It's a F limiting here into the displacement. How much the body is displacing? So by S into, so the F limiting is this side and displacement is right side. So the angle between them is 180 degrees, right? So the F limiting, what is the F limiting that we got? 10 into the displacement 5 into the cos 180 minus 1. So which is nothing but, so the minus 50 joules. So this is minus 50 joules. So the first option ruled out. The second option is correct. So this is plus 50. This is 250. No. So the option B is the correct one. Hope you guys understood the concept. So here force is applied this side and displacement is this side. So that's why the work done by the applied force is positive. But the work done by the friction is negative because the friction force is this side and body displaced right side. Okay, so if the force and displacement are opposite side, you can simply say that the work done is negative. Clear guys? Understood? Chalo. So let's go for the next question. So let's try this question on your own, everyone. So try this question. So vectors form, they gave it in the vector form. So let me write. See, so till now we have seen the work done is equals to F dot S, right? Or the work done is equals to Fs cos theta. Fs cos theta. So now see, if the object is originally at R1 position, and then the object is moved to some R2 position in vector form we are discussing about. Okay, so let's suppose this is some x1 I cap plus x2 j cap, y1 j cap. This position of this vector A, R1 is y1 j cap plus z1 k cap, and then this is having x2 I cap plus y2 j cap plus z2 k cap. So this is the R2, right? So therefore, so what is the work done in this case? So now the force is applied in this direction, let's suppose. So we know that the force is work done is equals to force into the displacement vector. Here S, R, we can also write it with R. Okay, so what is F dot here? R means R2 minus R1. Final, what is the displacement vector? Final minus initial, right? So that's why we should write R2 minus R1 vector, right? So which is nothing but here force into, so when you subtract this one, so we get x2 minus x1 I cap plus y2 minus y1 j cap, right? So plus Z2 minus Z1 k cap, Z2 minus Z1 k cap. So this is the work done by the force, where if the displacement is given in vector form, the position vectors of the particle is given. If the particle is moved from this point to some other point, okay, in 3-dimensional space upon applying the force, so then what is the work done means you can use this formula. So the next question is of the same kind. See here. So what's the question says here? So a force of 5 I cap plus 3 j cap is applied over a particle which displaces it from origin to the point, some other point. Okay. So let me take, this is the x-axis and then this is the, x-axis and y-axis. So originally the particle is at the origin, right? So then, so on the particle the force is applied. So now the particle has moved so to some other point. So let's say, so this is it has moved to this point, which is 2 I cap minus 1 j cap, right? So first let it be r1, let it be r2. So first let's find the what is the displacement vector. So the r vector is equals to r2 minus r1. So what is r2 here? Final position, which is 2 I cap minus 1 j cap, right? So minus, so initially it is at origin, so which is 0 I cap plus 0 j cap, origin means. So that's why the final r vector we got it is 2 I cap minus 1 j cap. This is the final vector, r position vector. So now they are asking what is the work done on the particle. So the work done will be equals to force dot displacement vector, right? So force vector is what? 5 I cap plus 3 j cap, right? So dot displacement vector is 2 I cap minus 1 j cap, right? So here we know the dot product, already we have seen it in the basic maths. So the I cap, I dot I1, j dot j1. So I dot j0, j dot I0, right? So that's why 5 into 2, 10 plus, so 3 into minus 1, 3. So 10 minus 3, so which is going to be 7 joules is a net work done. So the net work done is plus 7 joules. It's not minus 7. 5 into 2, 10 minus 3. So which is plus 7 joules. Option 3 is the correct one. Clear? Understood, guys? Everyone? Simple one. So let's go for the next question. So which was asked in NEET 2016. So what's the question says? See here. A particle moves from this point to this point. That means r1 vector is given, which is minus 2 I cap plus 5 j cap. And then r2 vector is given. So position vector 4 j cap plus 3 k cap. Okay. So when a force applied, so how much work has to be done? So the work done is equals to simply the f dot r. Here the force vector is given and r1, r2 vectors are given. First find what is the displacement vector r, which is equals to r2 minus r1 vector. So what is r2? 4 j cap plus 3 k cap minus r1 minus 2 I cap plus 5 j cap. So observe carefully, don't directly subtract 4 minus 2 is 2. So here it is j cap, here it is k cap, here it is I cap, here it is j cap. So first let's write, so let's do this way, 4 j cap plus 3 k cap, so plus minus of minus plus 2 I cap, so this is minus 5 j cap. So then let me write I cap first, which is 2 I cap, sorry guys, 4 j cap minus 5 j cap, which is minus j cap, and then next 3 k cap. So this is the work, the displacement vector. This is the displacement vector. So then the work done is equals to force. What is force? So the force applied is 4 I cap plus 3 j cap is a force applied into the displacement. What is the displacement? 2 I cap minus j cap plus 3 k cap. Okay, so then do the dot product. So I dot I, 4 into 2, 8, and then 3 into minus 1, 3, right? So therefore, yes or no, 4 into 2, 8, so 3 into minus 1, 3. So this is 5 joules is a work done. So the work done will be equals to 5 joules. Option 4 is the correct one. Clear, guys? Simple questions. So next one, let's try the 9th question. So what's the question says? A uniform force Newton acts on the mass 2 kg, hence the particle displaced from R1 to R2. Find the work done by the force. Same question. R1 vector is given 2i cap plus k cap, right? R2 vector is given, what is that? So 4i cap plus 3j cap minus k cap. So can we find what is the position vector, displacement vector, which is R2 vector minus R1 vector? What is R2? 4i cap plus 3j cap minus k cap, right? So what is R1? 2i cap plus k cap, right? So therefore I can write this as 4i cap plus 3j cap minus k cap minus 2i cap minus I am multiplying inside, so minus k cap. So here 4i minus 2i, which is 2i cap. So there is only one j term, so that's why 3j cap minus k, so minus 2k cap. So this is a position vector, right? So now we have to find the work done. The work done is equals to force into displacement vector. Yes, guys. So what is the force vector that is given in the question? A uniform force of 3i cap plus j cap. 3i cap plus j cap. And what is the displacement vector we got? So the displacement vector is 2i cap plus 3j cap minus 2k cap. So which is, so 3 into 2, 6, and then j, this is 1 into 3, 3. So 6 plus 3, 9 joules is a work done. 9 joules is a work done. Option 1. Clear? Understood? Chal. So let's move further. So let's take the next question. So the work done by the the question number 10, what they are saying? A body constrained to move in y direction is subjected to a force. Force vector is given and which is minus 2i cap plus 15j cap plus 6k cap. So the work done by this force in moving the object through a distance 10j cap. So that means the displacement is only in the y direction. So it is moved in the position vector is given, which is 10j meters. Okay. So along y-axis is, we have to find what is the work done. So the work done is equals to force dot displacement. Again the same thing. Force vector is minus 2i cap plus 15j cap plus 6k cap. Right? So dot displacement 10j cap. So here only j and j you have to multiply, remaining zeros will come. I dot j 0, k dot j 0. So 15 into 10, 150 joules. It is not j cap, it is joule. So the work done is equals to 150 joules. Option 1 is the correct one. Clear? Chalo. So now the work done by the variable force. So see here, let me take. So till now whatever the force that we applied is a constant force. Yes or no? So the work done is equals to F dot S. So this formula is valid when here the force is constant. Till now whatever we have seen, that is the constant force, like 5 newtons, 10 newtons, like that. So but along with the displacement of the body, if the force changes, let's suppose initially the particle is here, let's suppose, or else let's represent here. So initially the particle is here. Okay, some force is applied on it, so it moved to this point, and some other force is applied on it, so it moved to this point. So some other force is applied on it, that means along with the displacement, this is the displacement S, this is the force. So at this displacement this is the force, at this displacement this is the force, at this displacement this is the force, at this displacement this is the force. So that means, so the at different displacements we are getting the different forces. The force is variable now. If the force is variable, so then what we do? So here let me find, so the small work done at one place. So let's suppose here I am finding the very small work done in this portion. Let me find. So the very small work done in that portion, the dW is equals to, let the force acting at this point is some F force is acting at that point. So and then into, so let the small displacement in the here, let the small displacement, let it be ds. Okay, so that means I calculated, so throughout this is the total work done, right? So here I am finding the small work done in moving the from here to here. So that small work done is dW. How much force is applied? Some F force is applied. So how much it is displaced? ds. So similarly I'll find the force, what is the work done here, I'll find what is the work done here, and I'll find what is the work done here. So like that I'll find all the work done in small parts, here, 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 here. So and then I'll add up those work done. So this work done plus this work done plus this work done plus this work done till this point, right? So that I'll get the total work done. So the dW is equals to F dot ds. So then we can write, so the dW is equals to, I can write here the total work done. So to find the total work done, so to integrate, so add up all these small parts, we have the mathematical tool integration. So the integration of dW is equals to integration of F dot ds, right? So therefore the work done is equals to, so integration of F ds. So that means here, so what is integration means? What is integration means? Tell me. So integration is nothing but area under the curve. Area under which curve? See here, area under which curve? So force and displacement. So now here you should write that the area under Fs curve, the area under Fs curve, so results in the work done. So the area under Fs curve will result in the work done. Clear? Understood, guys? Chal. So now here one more thing. If the displacement vector is, if this displacement vector is some the displacement vector, let's suppose, so the ds are the ds is in x direction as well as in y direction, the displacement, and it is in z direction as well, if the body is displacing in all three directions due to the application of force. So then the work done will become, so the integration of F ds, right? So that means I can write Fx dx in the direction of x direction plus the integration of Fy, the force applied in the y direction, into the displacement in y direction. So the force applied in z direction, so just a minute. Chalo. So the force applied in z direction into the displacement in z direction. So therefore the work done, so here let's suppose it is displaced in the x direction from x1 to x2. So we can write Fx dx from x1 to x2. So and integration of Fy dy, so from y1 to y2 in the y direction, and then the integration of z1 to z2 into Fz dz in the z direction, in the y direction, and in the x direction. That means upon application of the force in the x direction, the particle is displacing in the x direction. So upon application of force in the y direction, the particle is displacing in the y direction from y1 to y2. So upon application of force in the z direction, so the body displacing from z1 to z2 in the z direction. That's the meaning. Clear? Understood this part, guys? Everyone? Clear? Sure. So let's move further. So now let's see this question which was asked in NEET 2019. So what's the question says? See here. A force 20 plus 10y acts upon a particle in y direction where F is in newtons and y is in meters. So the work done by this force to move the particle from y is equals to 0 to y is equals to 1 meter. So the force is acting only in the y direction, right? So the work done is equals to, we have the formula, let's write x1 to x2, write the complete formula, Fx dx. So the integration y1 to y2, so fy dy, and then z1 to z2, so z1 to z2 fz dz, right? So now, so the force is acting only in the y direction, they said. So that's why the work done in the x direction 0, the work done in the z direction 0. Yes or no? Yes. So the work done in the y direction will be equals to integration y1 to y2, so fy dy. So what is the force acting in the y direction? What is the force acting in the y direction? So this is the force which acts in the y direction. So integration from where to where that force is acting? 0 to 1. So the particle is displacing from where to where? 0 to 1. So what is this force? 20 plus 10y into dy. 20 plus 10y into dy, right? So now, so the work done is equals to, so the here 20 integration is 20y plus the 10 integration is 10y square by 2. Yes or no? So we already learned the integration, right? So from where to where this is? 0 to 1. 0 to 1. So the work done is equals to, I can write, so this is going to be 20y plus, so here it is 5y square. 20y plus 5y square. From where to where? 0 to 1. If you substitute the upper limit, it will become 20 plus 5 into 1 square means 5. And if you substitute the lower limit, it will become 0. So in place of y 0, if you substitute, so 20 into 0, 0, 5 into 0 square is 0. So that's why simply write it this one. So the work done is equals to 25 joules. The work done is equals to 25 joules. Clear, guys? So here the force is acting only in the y direction. That's why I took this. Done? Sure. So let's move further. So let's take the next question. So what's the question says? See here. A position dependent force. So what is a position dependent force? It's a variable force. See here. So 7 minus 2x plus 3x square acts on a small body of mass 2 kg, displaces it from x is equals to 0 to x is equals to 5. The work done in joule. Same kind question. So the work done is equals to x1 to integration x1 to x2 fx dx, integration y1 to y2 fy dy, and integration z1 to z2, so fz dz. So here the force is acting, the position dependent force only in the x direction. See here, there is no y term. So that means the work done by the work done in the y direction 0, so the work done in z direction 0. So and then here I can write the work done is equals to, in the x direction, from where to where it is displaced? 0 to 5. Integration 0 to 5. What is the force in the x direction? 7 minus 2x plus 3x square, right? So into dx, only in the x direction, right? So therefore the work done will be equals to, so what is the integration of 7 is 7x minus x integration is, so x square by 2, so 2 constant, so 2 into x square by 2, so 3 x square integration is x cube by 3. So from where to where? 0 to 5. So 2 2 cancel, 3 3 cancel, right? So therefore the work done is equals to, I can write 7x minus x square plus x cube. Yes, so 7x minus x square plus x cube. So 0 to 5. So now substitute upper limit minus lower limit. If you substitute the upper limit, 7 into 5, 35 minus, so x square, 5 square, 25 plus 5 cube, 125. And if you substitute the lower limit, it will be 0, right? 7 into 0, 0, x square, 0 square, 0. So 0 cube is 0 again, right? So therefore, so the work done is equals to, this is going to be 120, 150, 160, 160 minus 25. So 135, 160 minus 25, 135. Yes. So the work done is 135 joule. So the work done is 135 joule. Option 1. Clear, guys? Everyone? Sure. So now, so what is the work done by the FS graph? As we discussed earlier, so this is if the position dependent force is applied on the body. So then, so the work done will be equals to, so this is the total work done. So what is the total work done? The total work done is equals to the integration of F dot integration of F ds, right? So which is nothing but the work done is equals to area under Fs curve, area under Fs curve. So that means whatever the area here is there, so you have to find the area under that. So let's solve question so that you'll understand better. So see the question, guys, the simple questions. See here, what's the question says? So a force F acts on a particle moving in a straight line varies with the distance d as shown in the figure. The work done on the particle during the displacement 12 meters. So the work done on the particle during the displacement. So the force is acting from here, see here, from here to here. So from here to here. So the work done is equals to the area under Fs curve. Work done is equals to area under, here FD curve is given. Let's take FD curve. The displacement is given as D, right? So from here to here, see, this is a rectangle, and then this is rectangle, and then this is triangle, right? So area of rectangle plus area of triangle, right? So what is the rectangle area? So the rectangle length is 4 into the breadth is 2. From here to here, how much height? 2. So here 7 minus 3 is 4, right? So into, so what is the into, not into, plus half into base of the triangle 12 minus 7 5 into height of the triangle 2. So right, 2 cancel. So this is 8 plus 5. So which is 13 joules is a correct answer. 13 joules, option D. Simple questions, very easy questions, right? Chalo. So the next question, again the same question, I guess. A force acting on an object varies with the distance x as shown in the figure. So the force is newtons, x is in meters. The work done by the force in moving the object from x is equals to 0 to 6 meters. 0 to 6 meters. So first thing is the work done is equals to area under Fx curve. Here x is given, the displacement. So therefore let's write, so Fx curve. So then, so here one square is there, area of square, plus this one is triangle, area of triangle. That's it. So the first one, area of square. What is the square area? So side is 3 into 3 plus, so area of triangle half into base of the triangle is 6 minus 3 3, height of the triangle 3, right? So this is going to be 9 plus, so here 9 by 2, so which is 4.5, so which is nothing but 13.5 joules. So the correct answer is 13.5 joules, option 2. Clear, guys? Understood? Everyone? Chalo. So see, if the area is given, if the shape is downside, you should take this as positive area, this as positive area, this as positive area, these two as negative areas you should consider. Okay, so that's it. Only one question is left, or yes, only one question is left. So can you guys take this as a homework? Find the area of this triangle and find the area of this rectangle and find the area of this triangle. So add all these areas, and then from this, so add find the area of this triangle and this rectangle and subtract it. So that means let it be area of this one be A1, let it be A2, let it be A3, let it be A4, let it be A5. So then what the work done in this particular case will be equals to A1 plus A2 plus A3. So these three areas are above x-axis, that's why they should be taken as positive, and these two areas are below the x-axis. Let's take them as negative. So find the area of this triangle, this rectangle, this triangle, that is A1, A2, A3, and then A4 is triangle, A5 is rectangle again. So you can find the A4, A5. So but keep minus symbol for that. Okay, so you guys take this as a homework. Only one question is a homework. Okay, clear, guys? So we have seen the work done by the constant force, where work done is equals to F dot S, or we can write Fs cos theta, right? And work done by the variable force, so the work done is equals to the integration of F dot S, right? So or the integration of Fx dx from x1 to x2 plus the integration of Fy dy from y1 to y2 plus the integration of Fz dz from z1 to z2, if it is a position dependent force, that means the variable force, right? And area under work force and displacement curve results in the work done. Clear? Understood this concept, guys, everyone? So the basic concepts we dealt in the first class of work energy power. So in the next class we are going to discuss the work energy theorem, and before that we'll understand what are the conservative force and non-conservative force, and what is the work done by the conservative force and work done by the non-conservative force, and work energy theorem. So these are the two agendas for the next class, and I recommend you to solve more questions on today's discussed topic from any other reference. Okay, so and check your question solving skills. Okay, and write the short notes, start writing the short notes for this chapter from this lecture onwards. Clear, guys? So with this I am closing today's session. So let's meet in the tomorrow session. So that is work energy power lecture number 2. So till then, keep studying. All the very best. Bye, guys.